Well, hello everybody. I just barely made it home from work last night before the big blizzard hit. Yes, we got another big blizzard. First, I was driving home, and this is no lie. We hit a cold front. It was 64 degrees Fahrenheit, and as I started driving, the temperature started dropping as I hit the front. And literally 5 minutes, I went from 64 Fahrenheit to 39 degrees Fahrenheit. And by the time I got home, the rain was already turning into sheets of ice. And by the time I woke up this morning, there was almost a full foot of snow outside. So yeah, it's a good day to be down in the shop. So I thought I'd share something with you here. We're starting on our part 3, probably going to be our final part to the Sansui video, and I get a lot of questions about this transistor curve tracer that I built from the kit, how I use it, how it works, all these different things. So I'm actually matching some transistors. The owner asked me to replace the output transistors just to kind of make it future proof, and also the new transistors usually have a lot higher power rating, a little more durable. He just wants them. The transistors that are in here are functional. I, of course, don't know how well matched they are or anything anymore. I really didn't test them, but I'm going to take them out. I'm going to obviously mark them where they came out of in the receiver, and then give them to the owner so that he can keep them if he ever should want to go back to them. But I just want to go over real quickly how I do how I use this curve tracer. Now, if you go back on my video, I did one video on where I actually constructed this. I showed you where you can get it on eBay and so forth. And then on one of my viewer comments videos, I got into a little more detail of it, where to get the transformer and things like that. And then when I did the Verdun bell tower / Macintosh amplifier rebuild, I actually showed you briefly how I match transistors on it. But I'm going to get a little more detailed on it right now. So if that sounds good, stick with me, and we'll be right back. So the first thing you want to know about when you use this is kind of what these controls are. And these switches, if you go back and look at my video, they are connected to some jumper points on the circuit board. And very important, if you set this up incorrectly and you connect a transistor to this, you will fry the transistor. So this has absolutely no protection whatsoever on it. If you don't know how to use it, you will cook a transistor, and it's so fast that you won't have time to disconnect it. So you've been warned. So the first thing we want to know about is it an NPN or a PNP transistor? So you would select that, and all this is before you even turn the power on. There are two different power levels that have two different sets of test parameters. One is for power transistors, the other is for small signal transistors. If you connect a small signal transistor like a 2N3904 or 2N2222, something like that, and you have it set to power transistors, you will overload the transistor and it will fry. Conversely, if you connect it to small transistors, if you switch it down here and connect a large power transistor, it won't properly read. So you have to make sure you switch that correctly. In order to use this, you have to have an oscilloscope capable of doing XY mode. So, and this is the Y connection and the X connection. And for the Y connection, it's going to vary a little bit between 20 and 100 millivolts per division. And the X is always set to 2 volts per division. So this is going to be dependent upon the transistors that you're testing, how far they'll spread out you'll see the traces. So once you get that all set up, you connect your base emitter and collector to your transistor. Let me back up a little bit. And again, if you hook these up backwards, you can and possibly will damage your transistor. So make sure you get the pin out correct. You'll double, triple check before you hook this thing up. I'm serious. So let's hook one up. Oop, banging the camera here. Working around these cameras, I'll never get used to it. So we connect our base and our emitter on this particular transistor. Now these are these are MJ21194. They're an NPN power transistor. So we're just going to connect them up. I'm going to flip the power on. And then I'm going to go up here and I'm going to see if I can zoom you in closely enough without having to unmount my camera. Hopefully this will get you to where you need to be. Okay, and as you can see, I am currently set at 2 volts per division and 50 millivolts per division on the y-axis. This is important. 1 millivolt equals 1 milliamp is the way the scale is on this meter. And each one of these traces represents a different base current that it's applying. Is it base current or collector current? I'll have to look it up. Sorry, guys. And this is basically from your staircase signal that it's generating across the transistor. And each one of these, there's actually a written scale. And power transistors and small transistors, there's 2 different scales. So for instance, on this power transistor, the first scale is 0 mA of current. Okay. Just your base current, I'm sorry. IB is what it would be. Step number 2 is 0.32 milliamps, then 0.64 milliamps, 0.96 milliamps, 1.28 milliamps, 1.6 milliamps, 1.92 milliamps, and 2.24 milliamps. So to measure the gain of the transistor, you're going to go from, for instance, from our 0 point, and we're going to measure the amplitude to this top base current. Okay, we can use any one of these, but I always use the top one. It gives you the biggest number to divide by. So at 50 millivolts per division, each division is going to equal 50 milliamps. So 50, 100, 150, and then each little graticule is another 10. So 150, 160, 170, 180, about 185. Okay, so now we're going to take that 185 and divide it by 2.24, which is our test base current at this line here. So 185. So let's scroll down here and do the math. 185 divided by 2.24 equals, and you can see the gain of this transistor is 82.59, or about 82.6. So now that we know what that is, we shut it off. Go here, and I just write it down, 82.6. Okay, and that's really all there is to it. Now, when you go through a whole batch of transistors like this, you'll find some of them can vary widely and some of them are pretty close. So you can see, yeah, this one is 82, this one's an 82, this one's a 77, so these guys are kind of close. All of these are very close, 69, 68.5, 67.5, 67.9, and you can see they're pretty close. But what we want to do is, once we mark all these down, then we can pull them in groups and have a matched set. Now, again, when we hook these up, you'll see that amplitude of those lines will expand and contract based upon the gain of the transistor. So the higher the gain the transistor is, the higher the amplitude of your sweep will be. And if you don't want to use your calculator and calculate the actual gain factor, you can technically just use your cursor settings on your scope and set it, and you can just keep plugging transistors in until you find ones that match in amplitude, and they're going to match in gain. You don't know what the gain is because you didn't calculate it, but you know that the transistors, by comparing and matching the waveforms, have the same gain characteristics. So that's a quick and easy way to just match transistors, but you can also check the gain by doing the little math formula. So let's do one more. Okay, I have another transistor connected up. I turn it on, and you can see now this one, the amplitude is a little bit lower, so this is going to be a little lower gain than that last one. So you can see 50, 100, 150, and it's just below the 160. So we'll call that, say, 156, let's say, or 157. So we do 157 divided by 2.24, and this one is 70.08. So this transistor has a HFE, or a gain, of 70.08. So I'll take this one off and mark it and move on to the next. And that's the process. It's that simple. The thing I like about this curve tracer is that it actually puts real current and real power into the transistors. You can actually, if you leave this connected long enough, even on these big transistors, you can actually feel them get slightly warm. The small transistors you can really feel get warm if you leave them on too long. You don't want to leave them on for a really long time. So it's actually, unlike these little tiny battery testers here, you know, these are nice, but they don't technically put as good of a, you know, this just uses a tiny little battery. Actually, this one uses a 12 volt, looks like lithium battery or something, but it certainly does not have the current capacity and so forth of this. This actually uses a relatively large transformer in it that they require, and so it's similar to putting your transistor in a real circuit when you test it. So you'll see that the gain values that this will give you will be slightly different. Not totally, but slightly different from those little ones. And they seem to be more accurate and give you a more real world reading. So I hope that helps you on this. I'm going to go through and finish all these up, and I'm going to find a set of 8 that are very closely matched. I have a whole bunch of these. I probably have 40 or 50 of them, I don't know. But I'm going to go through till I find 8 of them that are very close. And then that way we know when we install these in this receiver, they're going to perform very, very well. One of the issues in these is these Sansuis and a lot of the bigger amplifiers use ganged sets of output transistors, meaning they'll have multiple transistors in parallel. And if they have too different of characteristics, it can affect how the amplifier performs, which is not a good thing. And it can also cause an imbalance between the transistors. So once again, that's why we match them. I'm going to finish this up. I'll get them matched, and then we're going to go back to the receiver, and I'll show you how we swap them out. So we're getting ready to replace these output transistors, and Sansui has a very unique type of heat sink from how everybody else does it. So first of all, you take 4 screws here, 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 and here off, and you remove this little outer cover. It's just a little metal cover and a little strip, a little warning strip or whatever you want to call that. We place that over here. Then it reveals a 2-piece heatsink assembly. So there's an inner heatsink and an outer heatsink. And in order to access the transistors, you have to decouple the 2 halves of the heatsink. So in order to do that, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 screws, and you take those apart, and then that reveals the transistors underneath, and they're actually very well socketed, very easy to replace and get in and out. Remember when you reassemble this, that in order for this part of the heatsink to properly couple to this part of the heatsink, you want to put heatsink compound on all of the contacting surfaces to get the best thermal coupling that you can get. And it's a really neat design. I kind of like the way they do it. So anyways, there it is. I'm going to take it all apart, and I'll show you the transistors once we get it all apart. So you can now see we have the outer heatsink assembly apart. You can see how they had it coupled with some grease, and it's getting kind of dried out and gross, so it was due for replacement. And then here's your 8 outputs, and as you can tell, if you take a look at the part numbers on this, and 2SC1116A, and there's all 8 of them are the same because this is a quasi-complementary output section. So instead of being complementary symmetry where you have 2 NPNs and 2 PNPs, 2 NPNs and 2 PNPs, they're all four are NPNs. So that's even more important that we get these properly matched. It's always important that you match them, but we want them all to be the same. So again, it would be interesting to kind of check these to see how well matched they are. I have a feeling that they were matched when Sansui put these together, because most of these companies, by the time you get to these higher end receivers, they went the extra step like that and made sure they beta matched the transistors and so forth. So this is probably a decent set of transistors. They are a lower power rating than the ones we're going to put in, and when transistors get old, especially this generation of them, they will fail over time. Not always, but sometimes. It's just kind of the nature, the kind of the processes they use today. They have a little bit better quality control, but these sounded very, very good in their day, and they worked very well, and these may work for many more years, but we're going to save them and make sure that the owner has them and make sure that he's able to put them back in should he ever decide to do it. So there we go. I'm going to get these out. I'm going to clean all this off, and then we're going to insert the new transistors. All right, well, I'm back here on the bench, and I got the heatsink off and got all the old transistors out and got all the old heatsink compound cleaned out. Took a little break, and last night we had our bowling league. My wife and I, we go out meet our friends, and we have a league on the weekends. And wow, hope I don't do as bad here as I did on the lanes yesterday. I'll tell you, I was about as graceful as an ostrich in a porta potty. Bad day for bowling for me. Anyways, that was yesterday. We're going to move on today. I got all the mica pads cleaned off. Strangely enough, when I went to take these transistors out, a lot of the screws literally I could just unscrew with my fingers. They were just finger tight. Some of the transistors, you could actually kind of wobble them a little bit in their sockets because they weren't tight. So I kind of think some of them have worked loose over the years, so we weren't getting really good thermal coupling. Even though the grease, there was thermal compound on there and everything, it was very dried out and kind of crusty and old, and wasn't even making good contact because the screws had worked loose and the transistor had worked loose in their sockets. So that's never a really good sign for the transistors. But anyhow, we're going to replace them. And we're still going to keep the old ones because they did in fact still work. I did not hook them up to the curve tracer, but I will just do a quick check on them with my transistor checker to make sure they're good, but I know they are. So we're going to get the new ones mounted up, get everything put back together neatly, and this receiver is going to be ready for a test and ready to do some alignment. And there was good news about the little transistors, the drivers, the KSA 1845s. I did get word from my shipper that a batch of them that I had ordered, I should have by the end of the week, which is great. But I really want to call out a few of the viewers who had actually heard my last video and came out and offered up to send some from their own personal stock that they had of them to keep this thing going. And I just want to thank you guys. You know who you are. Thank you so much for offering. I really appreciate that. So anyways, we're going to move on here and be able to give this thing a good test. All right, so we got it all back together and got a new glass put in the faceplate. Popped that in while I was at it, and have the thing turned on and warming up, and we're just kind of getting ready to do the bias and DC balance and start the alignment on this thing. And I will get those little transistors replaced, but I'm going to get it aligned first, and then I'll just have to touch that up after I replace those transistors. Obviously it'll affect it, but they're working right now, so I can move forward with all this. So we're going to let this thing run for a little bit, and then we're going to get the meters on it and take a look at the DC balance first, and then go ahead and adjust our bias. Okay, so this has been warming up for about 5 minutes or so, and we have this meter connected to the speaker terminals on the right, and we have this one up here connected to the speaker terminals on the left. So if you have 2 milliamp meters, it kind of makes things, or millivolt meters, it makes things a little easier because you can kind of look at both at once, both channels. And what they're asking for is 0 volts of DC balance, obviously, plus or minus 10 millivolts. So if you look here, that's where they say, just says to just put it on the speaker terminal, right and left channel, VR1 and VRO2, 0 volts plus or minus 10 millivolts. And if you look, we're already there on this. It's just a little tiny bit drifting, and we can kind of touch that up a little bit. And what we're really doing, for those of you who are kind of new to the sport here, is let's grab a schematic and take a quick look at what's going on here, if you don't mind taking the time. Essentially what we're doing here, let me back off a little bit, is you see we have VR01, and you can see it's just applying bias voltage to the base of this differential pair, which kind of all travels through here, and it's going to basically, you have your output transistors wired in here, and we're going to set those transistors up so that at the center point of those transistors, which is where your speaker terminal goes to with respect to ground, at null with no signal being applied, you want 0 volts there. 0 volts. It should sit totally at 0 volts, and in that way, when your input signal here swings positive, then you'll go from the 0 crossing to positive voltage, and when it swings negative, it'll go 0 crossing to the negative. And if there is an offset in there, if there is some sort of voltage other than 0 volts, especially when you're at the low volume levels, you'll hear that crossover distortion, and it will create distortion in the sound, especially like at low volume levels. Also at high volume levels, one of the DC rails, either the positive side or negative side, will max out and clip before the other one. So it won't clip symmetrically. So that's why it's so important to get your DC balance set properly. The closer you can get it to perfect, the better. So, you know, this is something you just have to kind of take your time and do a little bit at a time here till you get it dialed in. And they say plus or minus 10 millivolts, and you'll see it'll jump around. And you kind of have to move it a little bit. Okay, that's the wrong way, so we're going to go a little more this way. And see, that jumped. It's a very touchy alignment. And see, you just do a little bit of an adjustment and then let it settle. And then do a little more of an adjustment and let it settle. And you can see how it jumped from a positive voltage to a negative. We were going over that zero crossing. And you just kind of have to fiddle with it. There's about 2 or 3 millivolts there. That's pretty good there, and I don't think I'm going to mess with it anymore. See how it's kind of jumping through there? I think we're good. This one up here is already right where it needs to be. You can see it's sitting right at 0 volts. So yeah, I think we're in good shape. So let's go to our next step. Okay, hopefully I got all these in the shot. And as you can see, we're looking for we're actually in the F08 and F07 fuse socket. So you pull the fuse out of the socket and you put your meter on milliamps, and you put your milliamp meter in line with the fuse socket. So your meter is actually taking the place of the fuse. That way we can measure the current. And what they want you to do is they want you, for a model 9090, they're looking at 50 milliamps plus or minus 1 milliamp. For a model 8080, you do 30 milliamps. So you can see these are very low right now. We have them set way down. And don't worry about the plus or minus, because if I put the probes in backwards, it makes it, look backwards. So we're not worried about that. We just care about the number. So we want to get these both to be 50 milliamps. So we're going to take this first one. So this is the left channel. And we're going to try to adjust it. And it is not doing anything. Interesting. How about this one? That one adjusts. Okay, so we got this one. This one is not adjusting. Interesting. Okay, we're going to have to look and see why this is doing this. So it could be something with my test equipment or something else, but I'll be right back when I see what's going on. Okay, we have something wrong on this board, I think. And we're going to have to troubleshoot it because, number one, I can't adjust the bias with this pot. Second of all, this transistor right here is getting warm. It's not like burning my skin off my finger warm, but it is much, much warmer than all the others, and it is much, much warmer than the other channel. Now these two are staying cool. This one is a little bit above room temperature, you can touch, but definitely something going on down here. So we're going to have to look in the schematics and see what's going on, and we may have to kind of poke around in there and find out why it's doing what it's doing. This channel settled right in, and we got it right at 50 milliamps. It's good, but left channel, we're going to have to look at it a little bit more. So let me dig in a little bit, and when we find out what's going on, I'll be back. Well, little by little, we're zeroing in on some of the problems here. I want to just give you all a little update where I'm at. So on these driver transistors, this one and this one that was down here, which is this transistor, it worked when you would first turn it on. Everything was good with it, but if you change the temperature, either by putting some freeze spray on it or by it warming up, it would start to get a little bit noisy and start to act up. So obviously we had to replace that, and of course once you replace that, you have to replace its complement, because I did not have those exact transistors in stock. There are some in that package that you can still get, but I didn't have them. So I found these ones here that I do have brand new, and they're Fairchild. They're very good transistors, and they have higher power or higher current capabilities, so higher wattage capabilities also. But really they were well within the voltage specs. The gain, all those other things matched very well, so I used them. And something that was very handy that Sansui did is, if you look down in here, they actually put multiple mounting holes. So you can see there's 1, 2, 3, 4, 5 mounting holes for each transistor, so that if the pinout is different of your replacement transistor, you just simply mount it in the holes that allow the pinout to be correct. So that's what we did on these two. That corrected that issue. But still, on this channel, and of course, since I did it on one channel, I want it to be symmetrical, so I replaced, even though they were not testing bad on this side, I put the same components on this side to make sure it matched. Now, one of the other problems that I had is that still the bias on this side, perfect. And DC balance, perfect. On this side, DC balance is perfect. The bias, I still cannot get my 50 milliamps of bias current. I can only get it up to about 35 or 34 milliamps. And the reason being, and I tested all the voltages and components, everything is perfect. It's going to be this little 2SC 945, what is it, 984, I'm sorry, 2SC 984 transistor. And these are kind of a strange little animal here. If you notice, it is tied onto the heatsink of one of the driver transistors. And the reason they're doing that is they want thermal coupling between this bias transistor and your driver transistor, so that they kind of track together thermally. The problem with that is, this is a special transistor. I believe it's called a TO1 case, I think. I can't remember, but the thing that's unique about it is the case is actually an isolated case. In other words, the outer case of this transistor is not tied to the collector or to any of the other elements of the transistor, so that it can be directly mounted without any type of insulator. That poses a little bit of a problem, because any of the metal-cased replacement transistors out there normally would have the collector tied to the case, and the plastic-cased transistors, because actually a 2N2222 would be, as far as specs-wise, would be a really good replacement for this and would work very well. And you can mount that in there with some thermal epoxy if you can't get these, because these transistors, these 2SC 984s, are getting a little bit rare. You can buy them, but they price on them anywhere from $2 US up to $12 or $15 US each. And but we do have a solution, and I'll show you what it is without having to change anything. It just so happens I have several brand new old stock RCA 2SC 984s. And believe it or not, if you look right there, they're actually Hitachis. So these are original Hitachi components, brand new in the package. I have several of them left. Believe it or not, we used these a long time ago in a circuit in some of the old X-ray equipment, and that's how I have them. So we're going to replace that one transistor with an exact replacement, and I'm hoping that that will allow the bias to come in properly. Again, this other one is working properly. I can adjust it. I can see all the adjustment voltages when I test it in here, but it doesn't seem to affect, at some point in time this thing saturates, it doesn't go anymore, and you can't get the output. So I'm pretty sure at this point in time it is in fact that transistor. So I'm going to swap that last component out, and then we're going to see if we can get all the way up to our 50 milliamps of idle current. Alright, now, so I have this board out and it's completely finished. It is completely aligned and calibrated. The bias and balance are perfect, and this amp is just so, it worked so perfectly. I'm done. I'm not touching the amp anymore. Very, very happy with the outcome, and we'll look at some of the results here shortly when we're completely finished. But here's what all we did to this board, just a recap, because I know how much we did, and I'll explain to you what I found that fixed the bias problem on the left channel. So the first thing that we did was this transistor that was in here, which is this particular little guy right here, and that is a 2SA818. It was actually leaky. It was bad. So of course, replacing that with a different one that's compatible, actually superior design to the one that was in there, I had to go with the PNP complement of the same one. So I'm just using, believe it or not, I used an MJ 2955T and an MJE 3055T for the two complements, and they have 100 volt rating, which is very good because we got about 61 volts in there, and the old transistors had about an 80 volt rating. The wattage on the old ones was, I think, those like 10 or 20 watts. These ones are good for 90 watts. Everything else was very similar in the specs to them, so they worked very, very well. I tried replacing this when I couldn't bias it with a brand new old stock one. It didn't fix the problem, so I put it back. And of course, dummy me, down in here you see this brand new resistor, this little blue one. This is a 10 ohm metal film. There was a 10 ohm in there, and sure enough, when you pushed on it with the probe, it would go from around 10 ohms to 0 ohms, or to infinite ohms, like 1.2 meg or 1.5 meg. So this was a bad resistor. So I went ahead and I just replaced all those three metal film resistors. There was a 10 ohm, 150 ohm, and a 4.7 ohm, and you can see they're all brand new. And I figured if that one failed, it wasn't going to be long before these ones, so they got replaced as well. Obviously we did the mods where we put the fuses and moved this resistor, and we replaced these two resistors here on either side. I replaced those little differential pair transistors because if you remember, they had the real cruddy terminals on them and so forth, and I replaced them with a set of new old stock perfectly matched Fairchild KSC 1845s, and then I kind of fused them together with some, this is actually thermal adhesive. So what it is, it's thermal compound that's mixed with adhesive, so when it dries, that'll harden up. It will thermally bind these together, and then I covered it with some heat shrink. So I kind of made my own little transistor packages. And again, these were match sets that I put in here. They work very, very well. The audio path capacitors, these are low value ones. They got replaced with film capacitors, very good quality ones. And let's see, we replaced the pots with nice new ones. They are single turn, but they're really easy to adjust. And last but not least, these little gang diodes that were in here, they're notorious for going bad. You replace them with a pair of, in series, of 1N4148 diodes, and that corrects that problem. Any of the other film resistors or metal film resistors that could have been bad got swapped out. Obviously did the recap, and then went in and did a full alignment with letting it warm up and so forth, and it's perfect. So let's turn it on, and we'll just take a look at the oscilloscope here to see what kind of results we have now. Alright, I have both channels kind of superimposed over top of one another, so if these channels do not match as we increase the volume, it'll be pretty obvious because they won't overlap. But it should really look like one line, but there's actually both channels on top of one another. So here we go. And again, I'm not going to apply full power to this yet, but it is perfectly aligned. And you can see how nicely everything's tracking now. And right now we're sitting at about 50 watts per channel, according to the power meters here on the front. And you can see both channels are just perfectly overlapped with one another. So yeah, this thing's working great. I haven't done 100% of all the testing, but as it looks right now, this amp is going to be a really nice performer. So now the only thing left to do is to get into the receiver and do the receiver alignment. It is out. I just did a quick little check, you know, of it. It is tuning, and it does go into stereo, but it's definitely got some alignment issues. So we're going to try to get that straightened out, and maybe I'll take a little bit of time to explain a little bit about the test equipment a little bit on this, even at the risk of having a really long video here. But okay, so let's get set up for that, and we'll be back. Alright, by the way, I just remembered that I didn't show you something. When I did the recap and the replacement of the relay in here, there's a modification that needs to be done on this board to correct for a really catastrophic failure that could happen if the relay ever gets the contacts welded shut or something goes wrong with the relay circuit. And that is, there's a little jumper, and I just found it over here, and you can see there it is. And the jumper, if I do show you a little photograph, the jumper is, so here's the relay. The jumper is right here, see, right next to R06 resistor. See it? And that is these two little pads down here. And what you want to do is you want to just remove those pads. If you look down in there, this pad right here goes directly to chassis ground. This pad right here goes to one of the contacts of the relay. And what happens is, when that relay swings the one direction, it actually takes your speaker terminals and shorts them directly to ground. Now that's a bad thing, because if the amplifier is on, there is a possibility that this can toggle when it's not in protect mode, and it will actually cause the outputs of the amplifier to short out. It's a well-known issue with these 9090s, and take that out, and that'll solve that from ever happening. That'll prevent that problem from ever happening. So sorry about that, I forgot to show you that, but that's kind of important to see. So let's get this flipped back around then and do our tuner alignment. So we're getting ready to do another RF alignment on a receiver, and it always brings up questions. I get emails, I get comments, all kinds of things about how do you set up your test equipment. And I will tell you that the single most frustrating thing for me as I was learning how to do this was finding a good reliable source, or a book or a teacher or someone that could kind of walk me through how to set up my test equipment. Now, as I grew up at my older cousin's knee in his shop, a lot of times he'd set all this stuff up and I had no idea what he was doing. And a lot of people just kind of think you know it because they know it, and they just say, well, you just set up 10.7 megahertz and whatever. And the whole idea of decibels and all that didn't really make sense. And it took some time to figure it out. And you just have to work with it. You have to read a lot of books and talk to people who know what they're doing. Study the operator's manuals of your test equipment, especially your signal generators. But the biggest question that comes up is the whole question of dB and what it is. And I'll give you a little funny story. So my wife one time told me to go out and with my daughter and buy her a pair of jeans. And she said, I said, well, what size do I get? And of course she said something like size 6 or size 8. I don't know what it was. Some size. And I said, that kind of sounds like the same size that you wear, but your daughter, our daughter's young and she's a lot smaller. She's not fully grown and you're bigger than her, and yet how can you both wear the same size jeans? And well, of course, there's size 8 youth and there's size 8 petite, there's size 8 juniors and size 8 misses and size 8 plus, and so I'm like, wait, whoa, why are you doing this? And she says, well, that's rather than having a big range of numbers, they have different classes of clothing sizes. And I said, oh, so it's basically saying that, because with me, I don't know, us guys, you start at your waist and your inseam. So if you're a 50-inch waist, you're a size 50 pants. And if you're a 30-inch waist, you're size 30 pants. But that's not the way it works there. I said, oh, we have a similar thing like that in electronics, and we call it dB, or decibels. I said, really? I don't know why you guys come up with all these names. Why don't you just have your clothing size be in decibels, and then nobody will actually have a very large difference in clothing size? And she said, what do you mean? And I said, well, think about it. Get the very largest sized female you could get, and that would be 0 dB. Now, of course, we can't use dBf because that's taken up by decibel femtowatt, and can't use dBw because that's watts. But how about dBg for girl? So what the dB scale is all about, it's actually a scale that allows you to take a wider range of data, of numbers, and shrink them down into a smaller scale. So for instance, when you look at your spectrum analyzer, for instance, it would be very difficult to look at, for instance, a set of amplitudes from 0 volts up to like 100 volts. You could never fit that on a little screen or little display of a spectrum analyzer. So we scale those voltages by decibels, because especially like in radio, having a large range difference in voltage doesn't necessarily change the situation of the strength of the signal that much, not relative to the voltage. But when you move it in a logarithmic manner, which is what decibels is, decibel is a logarithmic scale, it makes it make more sense that you can move a set of numbers a very large amount with a very small multiplier. So back to our little example, I said, think about it. You take the very largest female clothing size and make that 0 dBg, and then think about it. By the time you got to negative 10 dBg, that would be a really small kid probably, if you go the sizes. So everybody could be about the same size. And think about it. I mean, hey, I was just on that new South Beach diet, and I'm already 3 dB down. See, us guys, we would understand that kind of lingo, right? So I hope that gives you an idea. All it is a type of scaling. Just like the women's clothing, petite and this, that, we have dBs up and down. And however, it's the letter that comes after that dB that's important, because dB in and of itself means nothing. It would say like how much, what is the power of that amplifier, and I'd just say 3. Well, 3 what? There has to be something that you're referencing it to. Decibels is the same way. Think of a decibel as just a number. But the number doesn't mean anything if the number isn't representing something. So that's why you see dBm, dBv, dBu, dBf, all these dBs, that letter that comes after it is what that decibel is referenced to. So for instance, when we talk about setting something to, minus 30 dBm, you're actually doing a logarithmic calculation of minus 30 dB with reference to 1 milliwatt. M is the accepted standard for milliwatt when it comes to dB. So when we talk about dBUV, that's microvolts. So that would be a dB logarithmic scale referenced to 1 microvolt. dBf is a dB scale with the reference to 1 femtowatt. Now all of these things are very important because if your service manual is telling you to set something, for instance here it says output 50 dB, well, dB what? If they mean dB microvolt and you set dB milliwatt, obviously the amplitude of that signal is going to be grossly different from what they're asking for here. Now, to make things more confusing, there's 2 things that make this a lot more confusing. Number 1 is when you look at our standard test equipment, so you look up here, and you've seen me use the HP a zillion times here, and why won't my camera focus? My camera's not focusing. Hold on. Don't know why the autofocus decided to wig out on me, but anyways, so here's the HP signal generator, and you can see, let me move these wires out of your way, that there's a couple things here. You have the numeric keypad that we can enter in whatever we want for the amplitude, and then you have to select the units that you want to set that to. And these units, most of them are only accurate if you have this terminated at a 50 ohm load. That means that if I don't have 50 ohms across this terminal, this reading here is not going to be correct. So why did they build it that way? Well, the reason being is in most cases, most equipment, radio equipment that we work on out there, whether it be ham radios or CB radios, they all reference to a termination of a 50 ohm antenna, antenna load. So you have to make sure that you choose the correct units. So if you look here, you have dBm, dBf, just straight dB, which is how you actually can change something by that amount, and EMF, which is electromotive force, which is just an open terminal output. You also have volts, millivolts, and microvolts. So these are power, units of power, wattage. These are units of voltage, or volts. And if you see these little lights here, it tells you what scale you're on. Right now we're on millivolts, so I have plus 5 millivolts of amplitude with reference to a 50 ohm load. Now the reason I keep saying that 50 ohm, that's really important. In most cases, you would hook your wire up to this, connect it to your radio, set it to whatever the manual says, and you're good to go. The problem is, when you work with FM, AM broadcast radios like this Sansui we're working on, the problem is they don't terminate their antenna at 50 ohms. They have 75 ohm termination and 300 ohm termination. And therefore, because you're putting a different load on your test equipment, this is no longer accurate. So you either have to calculate it, or you have to build an adapter. And they do make low loss adapters, but they are extraordinarily expensive, and you can't always find them online all the time, and you have to make sure it works with your test equipment. You can build little adapter circuits with a couple of resistors, and I'll show you an example of one if I have one here handy. Let's see, like here's one right here, and what this does is this will let you just plug it right into a 50 ohm coax, and then it goes through a couple of resistors and it adapts it to a 300 ohm load. But again, when you do that, there is a loss through those resistors, and you have to do a little bit of math to calculate the offset, through the loss. So what I'm driving at here is unless you have a dedicated piece of test equipment that was designed for commercial stereos, like what we're working on here, you're going to have to always be cautious of the output. Now, when you're just setting a frequency or you're peaking something, this being off a little bit doesn't really matter that much. But whenever you're trying to adjust a signal strength meter on your stereo, or the trip point for your muting circuit, or the trip point for your pilot and so forth for your stereo multiplex circuit, all of those things are very important. It has to be accurate or it's not going to work. And that's where you're going to have to do a little bit of fiddling around to get it where you want it. Now, that being said, to make it even more difficult, a lot of the things you see on my channel that I've worked on, like these old Pioneer receivers, Kenwood, Sansui, Marantz, a lot of the ones that were made in Japan, they had a very similar signal generator, but theirs was referenced to 75 ohms. And to make matters worse, they came up with their own little dB scale, and it doesn't match our dB scale. A lot of theirs is based on open terminals or based on 75 ohm. So you have to have a lot of notes. And if I back off here and I look at this, you'll see that I keep a lot of notes handy, and charts and all kinds of things to convert all the different scales around there. And one of the most important ones is when you're working on a Japanese receiver like this, and they start giving you this, let's go back down here, they give you this set it to 50 dB nonsense, and they don't tell you what dB they're referencing it to, like what value. Is it dB microvolt? Is it dB M for milliwatt? Is it, what is it? They just don't tell you. And to make matters worse, nowhere does it tell you what termination your test equipment is supposed to be set to for this to work. Now, they will give you a little circuit a lot of times to build that helps you to match. Let's see where we're at. Like if you look right here, they give you a little detector probe circuit, and sometimes they give you a little matching circuit. Right here, they're just telling you to come straight out of the output and go into a capacitor and couple it that way. And you see they use the word genoscope. Well, a genoscope is a special piece of test equipment that I don't have. And all it is a RF signal generator, a sweep generator, and a rudimentary oscilloscope all in one unit. I have separate components. I don't have a genoscope. So again, you have to adapt to whatever equipment you have. Now, a lot of times these companies, when they just give you the dB and don't give you any other information, a lot of times they're going on this scale right here. And when you look at this scale right here, you see if the Japanese signal generator is calling for 0 dB, what they're looking at is 0.5 microvolts. And that's microvolts into 75 or 300 ohms, depending on what terminals they're telling you to connect it to in the service manual. So if you go down the list here, it shows you 60 dB is 500 microvolts on our test equipment. So we're obviously going to be setting looking this chart up and then converting it to the voltage and applying that across there with a matched impedance, and that'll give you the signal strength you need. It's not easy. I'll just admit it. You have to keep a lot in your mind to make sure you get this set properly. So if that gives you a little idea of what we're doing. Now, once again, if you can get your hands on one of those Kenwood or Panasonic, there's several companies out there. I think Sound Technologies 1000A can directly do 75 ohm. A lot of those ones that you get from Japan, they are available on eBay. They're very expensive, and the shipping can be $200-300 just for the shipping, US. They directly have a 75 ohm output, and they have a dB setting that is correct. So if you had that and you just typed in 50 dB, you're good. But I don't have that, so I always have to be aware of that. Now, a lot of this stuff I do off camera, and because of that, you end up collecting all kinds of I literally have containers full of little adapter thingies that you make for all the different kinds of equipment you work on, and you need that. If you don't have that, you're going to have a really hard time with this. But again, the only time you're worried about that amplitude and the units of amplitude is really when you're doing something that relies on a certain exact level. For instance, doing the IF alignment, if it's not exactly 90 dB, they just want a strong signal. That's really what that is. And if it's not exactly 90 dB, no big deal. You'll still be able to align this. You'll still be able to get the waveform. It will still work. But when you get down here, where you start talking about they want this signal, this amplitude exactly, to equal this on a meter, now it's important, and you want to get that right. So I hope that clears some of that up, and hope I didn't confuse you more. But definitely, I'm not the world's pro at it either. I mean, I still have to think about it. I still make mistakes. I still have to sit down and look it up in the book, or kind of look up the formula or whatever for certain things. Because every time I work on one of these that's new to me, I run into some other situation like that you have to figure out what the manufacturer meant when they were saying to set it up this way, especially when you don't have their test equipment. All right, so let's, with that long-winded explanation, let's move on and actually put some of this to practice. Okay, let's see if we can explain where we are, what we have here. So the first thing we're going to do is we're going to align the intermediate frequency, or the IF coil, for the FM. And on the SG165 Sen core, I have a 10.7 megahertz swept signal with markers. And I'm injecting that right into the antenna coil, or in the antenna input. So you can see, here's my little matching pad coming from the signal generator, going right into the antenna terminals up here. And you can see down here, I have the little matching pad, the detector probe. And the detector probe is going into the from detector jack on the 165. So if we go up here and zoom you in, you can see where we're at. So this wire that says from detector is going to the detector probe. This wire that says all signal output goes to the matching output pad into the antenna. And then the one that says to scope is going over up here to the oscilloscope. And you can see they want you to connect on test point TP01, which is right next to the coil that we're going to adjust. And that coil is actually called coil T01. So that's the transformer 01. And all I'm going to do now is I'm just going to adjust to get maximum amplitude out of that. So probably it's already there because this receiver was working, but we're going to adjust it and see where we are. So you can see there's our signal. And I'm just going to put the adjuster in here, and we're going to tweak it and see what happens. Okay, there it's going down. And wow, look, we're getting a little more out of it. And you can see as I run through that null point, it peaks out and then starts going down. So I'm just going to rock this adjustment back and forth until right there. So that coil is peaked out. All right, we're now going to go on to our next step. So pretty much this is going to be the whole process through the whole thing. And again, I did not set this to 90 dB and 50 dB. It's really not necessary. I just needed a signal that was strong enough to get the IF signal in there. Okay, let's look at our next step. Okay, now we're going to do the next coil, which is transformer T04, and we're going to do TP04, and we're going to have a very similar signal up here, and we're just going to do the same thing. So let's adjust this and see if it moves up on us at all. Okay, wrong way. Oh wow, got a little bit more out of that one too. Okay, very good. All right, so now let's look at the next thing. Okay, the next thing we're going to look at is our discriminator coil. And again, there's all kind of crazy things in this service manual. The first thing they talk about, let me just show you, pictures worth 1,000 words here. They talk about, when doing the discriminator, they want TP03. And we're injecting the signal into TP01 of the FM-AM pack. So we're basically injecting it up in here on the underneath of it. There's a test point, and you just attach to that. But down here, they're talking about we're going to measure it at TP03. Well, there is no TP03 on this particular board. Now, there may have been at one time. But if we look on the service manual here, here's the board, and you can see TP03 is clear here down here at the bottom of the board. So if we hold the board this way, there's TP03. So you have this integrated circuit, and you have the de-emphasis switch, TP03. Here's the de-emphasis switch. Here's the chip. And right in there is where it should be, and there is no TP03. But on this one, there is actually a little header plug. And if you kind of zoom in down here, you can kind of see it. If I move this out of the way, you can see that little header plug right there. And this top pin is the one you want to attach to. And don't ask me how long it took to figure that out. And as you can see, there's your S-curve for the discriminator. Now, the idea of adjusting an S-curve is when we do our S-curve, we want, let me adjust it here. If I crank up the markers, you can see where my markers are here. And right here is your center marker. And then there's your plus and minus markers on either side. And I think that's like plus 200 kilohertz on either side. I forget. I'm a terrible teacher, huh? So here's your three markers. And the idea is to get this to be, first of all, we want this to be symmetrical. We want the center marker, which represents your 10.7 megahertz, we want it to be right at the zero crossing. And then we want our side markers to be halfway between this marker and this peak, and the 10.7 in this peak. And you can see how close they are already. And you can see that I have my trace, my zero crossing set to the center graticule, and we're on pretty close. So what this means is that the discriminator is most likely going to be already adjusted. We're not going to have to play with it too much. Now, if we did need to adjust it, we would want to adjust the two coils T02 and T03, which are these two guys right here. And adjusting them is what adjusts the symmetry and centering and all that of the coil. So if I turn one here, I'll just show you how it affects it. You can see that it'll throw the whole thing off, up and down, and the other one kind of will distort it. Hold on a second. See how it kind of moves it around? And the idea is to get pretty close to the same symmetry on, right, like that. You want it to, the slope, you want it to be nice and straight and even. So you want a straight slope. You don't want it to be shifting. You want this to be a nice straight slope like that. You want this to be centered, and you want these to be centered. And you can see we got it pretty close. It's not bad. So, and of course, I recapped all this. So, including the 10 microfarad capacitor that goes across the discriminator. That capacitor is really critical because it will cause this curve to be incorrect. So this is also a good sign that you know, that our capacitor is actually doing its job. And so that's it. I mean, discriminator's adjusted, pretty happy with it, and we're ready to move on to the next adjustment. Now we're going to actually start dealing with frequencies. Now that we got the intermediate frequency working well, now we're going to actually do the RF alignment, where we're actually going to align how the dial accuracy and all that sort of stuff. So that's our next step. So let's get set up for that. All right, for our next adjustment, we're going to adjust our 90 megahertz dial accuracy. And so in order to do that, we've kind of gotten away from the SG165 right now, because even though it's pretty close, I like the digital accuracy of the 8657 HP. So we're up here on the 8657, and you can see I have 90 megahertz. They want FM modulation, and they want 100% modulation. That's what they're asking for. And they want plus 60 dB. Now I have it set to 60 dBf, which is femtowatt, and it is not accurate right now because I do not have a proper matching pad, nor am I using the correct offset. But I am using a 300 ohm balun. It's not matched, so don't even think that. So it is not an exact signal going in there, but it's not important for what we're doing right now. We want a signal to tune into. That's all we're looking for right now. We don't want it to swamp the tuner, and we don't want it to be so weak that it creates a lot of noise. They just want a nice medium strength signal, and that's what we've got in there right now. So we're just connected to our antenna terminals, and the oscilloscope, I just have a set of RCA adapter jacks, RCA on one end and BNC on the other, and we're just coming out of the tape recorder record out jacks, and we're going up to our oscilloscope. So you see it up there, and all you're looking at is our 400 hertz modulation tone coming out of the record jacks. And the name of the game here is to tune the radio dial. So if we come over here and we look at our radio dial, we want that to be right on 90 megahertz. And if I scroll down, you're at an odd angle, but this is absolutely dead centered over 90 megahertz. And if all is well, we should be perfectly tuned right here onto the, you should see a nice clean undistorted modulated signal. Now watch what happens when I go off tune. I'm just going to turn the tuning knob. See what happens? It starts to get distorted. I'm just sweeping back and forth over that 90 megahertz. So what that's telling us right now is our 90 megahertz adjustment is perfect. So if it were not perfect, we would have to adjust coil L06, and that's on up here. So right here on the tuning gang, all right, you have L06, which, if we look that up, would be this one clear on the end down here. So we would adjust that slug. And essentially all we're going to do is we're going to go through, now we're going to set 106 megahertz the same way. And we're going to adjust TC04, which is one of these in here. Same thing. We're going to make sure that it's dead centered over the 106 megahertz on the dial. We're going to change our signal generator to 106 over here. So just go one frequency 106 megahertz. And you can see I'm going to tune it now. And when my tuning dial gets over 106, you can see there it is. Right there. And I'm just a tiny, teeny, little tiny bit off. Right about, I'll put it on where it should be. Should be right about there. And what we want is TC04, which is this one right down here. So we're going to adjust this little adjuster right here until that's perfectly undistorted. So you can see, and it is very, very touchy, and I'm using a non-magnetic, and you can see there it is. And I'm using a non-magnetic, just a ceramic adjuster, and that's it. So now our dial accuracy is set. Now it's usually a good idea to go back and forth between the 90 and the 106 a few times until you get it perfectly centered. All right, so that's your dial calibration. And then we're going to go through and we're going to do 90 and 106, what they call the RF calibration. And that's just to get everything peaked out so that it's, you know, perfect. And that's it. We're done. That we'll go on to the signal strength meter, and then we'll adjust the other part of the discriminator for minimum distortion. And then we'll be ready to go on and do our multiplex. So you get the idea of how the alignment goes. Basically, you're connecting your test equipment, setting it, and then, you know, adjusting the slug. I'm probably not going to go through each and every step because this will be an epic length movie by the time we're done. But you get the idea of how this all works. So I'm going to do a couple more of these and skip ahead, and then when we get to the multiplex, I'll come back and we'll come back. All right, so we're getting ready now to do the multiplex alignment, and that's for our stereo. And the first step we're going to do is the PLL voltage controlled oscillator, the VCO. And in order to do that, they want 98 megahertz on the antenna input, 60 dB, which in Japanese conversion terms would be 500 microvolts, so kind of a medium strong signal. And they want us to put our 19 kilohertz pilot, which of course that 19 kilohertz pilot, if you go back a few videos, you'll see where I described what that is. That's actually what tells the multiplex circuit to activate that it's a stereo signal. And we want that at 10% modulation, and we want our left channel turned on. So we want a 1 kilohertz. I have actually a 400 hertz on my SG165 modulation on the left channel and no modulation on the right channel. And you can see they basically want you to adjust that until the stereo indicator comes on. And we're going to adjust VR04 on the tuner board. So if you kind of, let's see if we can get down there far enough to see, and we cannot. Let's see, can't get down in there. Okay, hold on a second. Okay, I have a new camera mount, and for some things it's really good for positioning the camera for doing these videos, but one thing it does not do is go up and down like this, and I can't get at the right angle with this thing under here. So I'm going to have to do some shaky handheld camera. What we're going to adjust once again is VR04, which just so happens to be this little blue pot right here. You can see it. And I'm just going to adjust it. Again, I have my signal generator set up. I have a wire going into the external modulation input, and that's coming from the SG165's output, and the SG165 is set to the multiplex signal, and you can see I have the 19 kilohertz up there selected, and I have right channel on, left channel off. So all we're going to do, and again this is already adjusted, but I'll just kind of give you an idea of what happens. And if we move this pot the wrong way, you'll lose your stereo. You see that? So all we're going to do, kind of hopefully catch it all in the video, we're going to rotate this until we get the stereo signal back. You can see. So off, on, right there. And that's right about where it needs to be, right there. And then if we tune off of it, we lose it. We tune back onto it, right there. So simple as that. All right, next. All right, the next step is to adjust our stereo separation. And this time we're going to have the left channel turned off and the right channel turned on. Okay, so we're just swapping them around. And we're going to go onto the antenna terminal. Same thing. And we're going to just look at our left channel. And what we should see when we look at the oscilloscope, one channel should be off and the other one should be on. And we're going to adjust VR05 for the minimum output on the channel that is not turned on. So if the multiplex circuit is working and aligned properly, you should have a pretty full signal on one channel, the one that has the modulation on it. The other one should be pretty much a flat line. It's not going to suppress it 100%, but you want to minimize it. So, and we're going to do that by adjusting VR05, which is this, let's see where it's at. VR06, I believe it's this one right here. We're going to adjust. Oh, I'm sorry, VR05 right down here. So I'm just going to adjust that, and I'm going to put you back up here on the scope and let you see what we have here. And you can see how that's pretty much a flat line right now. So it's pretty much in line already, but let's throw it a little bit out of alignment just so you can see what it does when it's wrong. Okay, so you can see if it's misadjusted, you don't have complete stereo separation now. You're getting some bleed over. And if I turn the pot the other way, I can flatten it out. And if I keep going, you can see it comes back up again. So we kind of run it through that null point. And the idea is to adjust it till it's as flat as you can possibly get it, which is right about there. Okay, so that's all set to go. So now we have our separation set. Let's go to our next step. Okay, the next one, it's our distortion adjustment. Everything is going to stay the same. with the exception of we're going to put the distortion meter in, and I already have it wired up, and we're just going to adjust this coil, and it's a two-slugged coil. It's got an upper and lower slug, and that is over here, and it's this one right here, and we're just going to take this little tuning stick and we're going to adjust them for minimum distortion. Now you're going to find out that this is kind of, I didn't fuss around with my distortion meter to get it minimized total, so I'm not going to take a quantitative measurement of the distortion, but I'm just going to, we're basically going to use the slugs to minimize the distortion as low as we can. And I think we're already there, but we'll go up there and I'll kind of show you how it adjusts it. So if you look up here, right there, there's our distortion meter, and you can see how it kind of bounces around. And all we're going to do is we're going to adjust these two slugs for minimum distortion, and you'll see as I turn it, see how this distortion is going up? See, it's going up, and right about there is about, and again it's real bouncy because of all the noise floor and everything in there. And then we do the other one, and you can see you just kind of drop it. That's about all I can get out of it. You can see how it bounces around. And while you're at it, you can kind of look at the oscilloscope as well, and you can look at the waveform there. So kind of between the distortion meter and the scope, you can kind of get a feel for when you get it. And there you go. All right, now we're going to do stereo separation on the other channel. You can see we're going to turn this one off, and we're going to turn the left on. So now we're looking at left channel modulation with no modulation on the right, and we're going to do VR05 again and minimize it back out again. So let me change my scope a little bit, and again, you're still adjusting the same pot, but they're just going to make sure that you're kind of doing the happy medium between the two. And you can see it's flat. We really don't have to touch it. That's about as flat as you're going to get it. Now, if it were a little bit on there, you could null it out, and then you would kind of go back and forth between right and left channel till you got a good compromise between the two. But I think we have that one in there pretty good. So next, last but not least, is our muting. And all the muting is doing is you're just putting a weak signal into there. 23 dB is going to be just a little bit under 8 microvolts, I believe. Yeah. And when you put it in there, you should hear, it'll get, like, you can hear how clear the sound is right now. I'll turn on both channels. You can kind of hear that. And again, they just want one channel. So what we're going to do is we're going to move the signal way down. So amplitude. And you can hear just how staticky it gets. And you want it to just be on right about there. And you can see that what's happening is your stereo is toggling on and off. And the muting is just ready to kick. So all we're going to do is we're going to adjust VR03, which is this pot right here. And what you want to do is you want to adjust it, and it's already there. If I go down one step, you hear that? It kicks out, and it goes into FM muting. I have the FM muting turned on right now. And if I go back up, it comes back on. And that's really what they're looking for. So you're just setting the level at which the muting control kicks in and mutes your FM off. With that, that is the end of the multiplex adjustment. So now our FM is adjusted and our multiplex is adjusted, and everything's coming right into spec. Actually, it's tracking pretty well. Now again, I'm doing this with my test equipment, and of course they show a different setup of test equipment in the service manual here, and you may have something different also, so you kind of have to adapt once again your equipment to this procedure. That's really the trick on this. When you work on a lot of different manufacturers of equipment, you can't possibly have every piece of test equipment for every for every factory alignment. So you have to learn how to generate those signals with the equipment that you have. So I hope this little run through helps you out with that a little bit. So now we're going to do the AM, and that's very basic. I don't think I'll do that on camera. All you're going to do is set the IF for 455, and then you're going to, it's the same thing as the FM. You're going to set your dial accuracy at 600 and 1400 kilohertz, and then your RF, and then your antenna adjustment, and then you're going to adjust your signal meter. I'm kind of surprised they don't have you adjust the slug inside the antenna, because there is one there. They actually don't have that in there. Let me see. Bar antenna, yeah, right here on the 600 kilohertz RF adjustment. You adjust the antenna. So you guys have seen me do that already. So I'm just going to do that one off camera. It's just AM radio, very simple. And this thing's finished. We're going to do a little bit of cosmetic cleaning, put it back together, and it'll be ready to do a little test, and we'll be wrapping this video up. Alright, so I don't have very good reception down here, I think, as I've said a million times, but regardless, let's just go through the dial a little bit and just see if we can pick up some stations tonight.
Yeah. I'll bet you there's a lot of wives wondering.
The world awaits.
And if we turn the muting on,
Showcase presented by Triple.
Jerry Taylor Ford on Route 58.
In business loans.
Mercy.
so you get the point. So you get the point. Tuner's working perfectly. Very happy with it. So yeah, this is turning out to be a really good receiver now. So let's put the covers back on and let's do our typical, like we always do, our traditional power test. See what kind of output this thing has, and then maybe we'll hook up a set of speakers and see how it sounds. Well, here's the finished product all put together. And so I've got the oscilloscope connected and the signal generator, and I've also got my THD meter, and we're just going to check and see what kind of power and what kind of harmonic distortion we're going to get out of this thing. So let's check it out and see. Okay, let's just go over this a little bit. Right here is reading the RMS voltages, and this is where we're going to be able to calculate the wattage. We can see the oscilloscope, so we can actually see the sine wave that's coming out, across the dummy load. And up here, this is total harmonic distortion. I have my Keithley 2015 set up for the THD display. So let's crank this up and let's see what it gives us. Alright, there's 32.2 volts, and we're sitting at 0.042% distortion. You can see there, that's 0.043. 32.2 volts RMS. So let's calculate the wattage from that. That's 129 watts. Not bad for an amp that's was rated at 110 watts. So we're getting almost 130 watts of power at 0.045% total harmonic distortion. I would say that this amp is working really well. I am very pleased with the way it turned out. It looks beautiful. I really like the blue display on this thing. I like the way the warm white LEDs kind of set off the power meters now. I like the blue LEDs in behind the signal strength and tuning meters. That's a beautiful looking receiver. The cabinet cleaned up pretty good. I mean, it has some chips on the side and so forth, but hey, for something this old, you can't really complain a whole lot. I don't know if I'm going to be able to hook this up to the big speakers. I have quite a bit of projects going on over there to test it, but this would be a good one to do the demo on. But we can hook it up to our little bench speakers and put an MP3 player on it just to see what it does. We got to at least hear something come out of this thing, huh? So let me do that at least, and then maybe before I wrap up the video, if I can, I'll think about it overnight, and maybe we'll connect the big speakers before I pack this up. Well, of course, we can't play anything good for very long without getting dinged, so I'll just put this on a little bit. This is a kind of a cover tune that I have here by an artist named Gloria Estefan, and it's called It's Too Late, and I'm just kind of a little bit into the song a little bit, but we'll play a little bit of it just to hear. This is kind of a pretty decent recording, so of course we got all the furnace and everything going in the background, and we're using the camera mic, but gives you an idea of what it sounds like, I guess. Here we go, just for a few seconds.
It's changing, or maybe we've just stopped trying. And it's too late, baby, now it's too late. Though we really did try to make it.
Sounds pretty good. It sounds really clear. I wish you guys could listen to more music on this, or I wish the YouTube library would come out with some more nicer songs or something. It'd be really nice to demo some of this stuff a little more. But anyways, thank you so much for coming along with me on this epic length video and this really major restoration here that we did. I hope you enjoyed watching it. Hope you learned a few things. And as always, I thank you all for watching, and I wish you all the very best of health, peace, joy, and happiness in your lives. And thank you all once again for all your kind words and comments, and lots of more to come. I got a couple more receivers to go up on the bench. I have a couple other little videos I'm working on in between all the things going on at work and at home and all that, but we'll get some more stuff out there. So till next time, thank you all, and till next time, take care. Bye-bye.